Hey guys, I'm getting some questions about the last problem on the optimization homework, which is awesome because that means some of you are on the last problem of the optimization homework. So this is one that I would normally go over in class because I get asked it every semester. Honestly, I have it picked in there because it's a good refresher of our derivative rules. So you're given a C of t, and I'm going to make it up so that it's not the same as any of yours, but it can help you through the homework. So I'm going to say my random C of t, I'm going to say is 1.5 t e to the negative 2t. It's something like that. You'll have different numbers, so don't be offended if this is not your number. It probably isn't any of your numbers. So we want to do optimization for this. So without going too much into the details of the problem, I just want to show you math-wise what to do. And then you can kind of interpret on your own. So we want to do our two steps. The first step to optimization is to find the critical numbers. We need to take the derivative of this. And this is like the whole reason I picked this one. It has a couple good rules. So first of all, we have 1.5t times e to the negative 2t. So we have t's that are multiplied. We're going to have to use the product rule. So good review of that. The other thing is we have e to a power that's not just a regular x or a regular t. So it's also a review of rule 6. Which comes up a whole bunch, but it is for some reason kind of forgettable. So rule 6 is like if you have e to any power that's not just a regular x. So just reviewing this, how do we do e to the x cubed? We do the derivative of the power times e to the original power. So this reviews two things, the product rule and rule 6. So we're going to use both in this. So first of all, the product rule, derivative of the first times the original second. So derivative of 1.5t is 1.5. Original second is e to the negative 2t. Derivative of the first, original second, plus always the derivative of the second times the original first. And this is where I'm going to use rule 6. Derivative of e to the negative 2t is going to be the derivative of the power. Derivative of negative 2t is negative 2. Times e to the original power. So derivative of the power times e to the original power. And now we have to finish up the product rule. Derivative of the first, original second, plus derivative of the second times the original first, which is a 1.5t. So good review of our rules. And I want to set this equal to 0. So in order to do this factoring, I might want to multiply some things out. So this first piece is good to go. I have 1.5 e to the negative 2t. Not much I can do with that. But the second piece, I'm going to grab my calculator, and I'm going to see what negative 2 times 1.5 is going to be. So you're going to have some random decimals of your own to do the same thing with. You want to multiply them out. So negative 2 times 1.5 is going to be negative 3. So I end up with negative 3t, because there's still a t from over here, e to the negative 2t. And I'm setting this all equal to 0. So you take the derivative using the product rule and rule 6, no matter what your numbers are, and then you want to multiply any numbers together that you can. Here I had 1.5 e to the negative 2t, and then I multiplied these decimals together and I got negative 3t e to the negative 2t. And it's okay if you still end up with a decimal there. So my next step is to factor this. So this is just some weird factoring. I want to take out my greatest common factor, which is just going to be this e to the negative 2t. So for my numbers, there's actually more than that I could take out, but I'm going to pretend like I can't, just in case your numbers you can't take out a constant as well. So we're just going to take out the e term and figure out what it's multiplied by. So e, to get back to the first term, is a 1.5. And then this e term is multiplied by a negative 3t for the second term. And we're setting that equal to 0. So the thing about e to a power is exponential growth never equals 0. So if it was exponential growth, it'd go up like this, and it would never touch 0. This one's actually to a negative power, so it would be decay. But this e never equals 0. E to any power will never, ever, ever be 0. So really, you end up having to solve a linear function. Your other term, 1.5 minus 3t equals 0. You want to solve this for t. So you're just going to solve it like linear function. You're going to get t by itself, so you could subtract 1.5. You have negative 3t equals negative 1.5, and then divide by negative 3. And you have your t value. This is your critical number. If it is on your interval of interest, you'll have to test it to compare your y values. If it's not on your interval of interest, you don't even have to test your critical number. So mine ends up being 1.5 divided by, or negative 1.5 divided by negative 3. Two negatives cancel out and make it positive, and I get 0.5. So if we're looking between 0 and 5 hours after drinking alcohol, we would have to test it. So it would be on the interval. Whatever interval you're given, you want to test your bounds. Whatever you're given, your 0 is your initial time that you drink, 5 hours later, and then test your critical number in between to see what the blood alcohol content is, comparing these. So you can figure out what the maximum blood alcohol content is, that's the y value, and then the x value, the time that it takes for it to happen, how many hours later. So this is just a general example. I would take notes on this, write this down, and then try it with your numbers, because you might have some different decimals that end up being a different way, but you are all going to have a product rule, and you all have to take out this factor of an e, which can never be 0, and then end up solving this linear function. So this kind of gives you the general pattern, and I hope it helps.